Assalamu alaikum, everyone. Welcome back. So in the last class, we were talking about the reaction rate coefficient or reaction rate constant, and we saw that using the Arrhenius equation, we are able to write a formula for reaction rate constant or coefficient, relating it to the pre-exponential factor or the Arrhenius factor A, and the activation energy, which is in the exponential form here. So we also solved a very simple problem here where the pre-exponential factor A was provided, the activation energy was provided, and using the simple Arrhenius relation, we came up with the reaction rate coefficient, right? So this is normally done when you have these the values available already from previous measurements. We also briefly discussed the limitations of Arrhenius equation and the flexibility of using modified Arrhenius equation, which has this temperature raised to n part, where n can be from -1 to 1, and this just brings more flexibility to the basic Arrhenius equation and allows us to use it to fit more reaction rates. Okay, now let's do another very simple problem, and then we'll discuss more topics after that. Now, in the previous problem, we're having the same formula, the Arrhenius formula, where reaction rate coefficient is equal to A times exponential minus activation energy by RT. Okay. In the first case, the pre-exponential factor and activation energy was given to you, which is something we obtain from experiments, right? It's not measured directly. Now, in this other problem, what we are going to do is actually we are using the experimental data, which in reality is just at different temperatures, you measure what the reaction rate is, okay, by looking at the concentration decay of the reactants or the production of the or the time history of the product formation. Okay, so basically you track the reactant concentration. Let's say the reaction is A plus B giving C plus D, so you can track how the concentration for one of the reactants is varying with time, and you set it up using the reaction rate formula, which is dA by dt is minus K times concentration of A times concentration of B. We will be able to back out the value for K, right? And so you do this at different temperatures, like shown here, 400, 500, 600, all the way to 1000, and you have a different value for K measured at every temperature. Now, the task is based on this experimental measurement, okay, we want to come up with the exponential factor and the apparent activation energy, right? Which is the activation energy that is part of the Arrhenius equation. So this is the Arrhenius equation we're looking at, and log K is going to give you log A minus activation energy by RT. Now, when you plot log K on y-axis versus 1 by T on the x-axis, what we get is a linear line, okay, a linear plot, and this is 1 by T and log K, x and y axis, and the intercept of this line is equal to log A. So log A here for this particular case is equal to 27.393, and the slope of the line, which is this part right here, is equal to the activation energy by R. Okay, 1 by T is the x-axis. So activation energy by R is equal to 9882.3. Okay, so once you have these numbers, I can find activation energy by simply multiplying this the slope with the universal gas constant, and when I do that, this is the value that I get, and I can get the activation energy by simply taking exponential of this number, right? Exponential of 27.393 will give me this number. So this is really, really simple. This is basic math, right? But this is how essentially you start from a measurement and end up with Arrhenius coefficient, the Arrhenius factor or the frequency factor A and the apparent activation energy. And once you have that, okay, once you have these for measured numbers, then it can be used for anyone else can make use of this for calculating the reaction rates in the range at which it was measured, right? Which is 400 to 1000 Kelvin here. Okay, so having discussed this, let's move on and let's talk a little bit more about elementary reactions. Till now, we started looking at the reactions and we spoke about different ways in which a reaction progresses. We looked at the law of mass action. We looked at the rate law, which essentially tell us something about uh, the reaction rate and what it depends on. And the law of mass action, we said, applies only to elementary reactions. And in reality, most of the reactions that we see around us, they proceed through a series of elementary reactions, right? So the focus of this current chapter on chemical kinetics and mechanisms is actually on understanding elementary reactions. And we have been doing that slowly and surely for now. And we just want to take it to the next level by classifying these elementary chemical reactions. Okay, so they can be classified based on several criteria, some of which is mentioned here. Depends on the direction. We can classify them based on the direction of reaction, molecularity, whether they are consecutive or not, whether they are competitive or not, chain reaction, and even the phase of the reactants. Now, we will not talk much about the phase of the reactants and products simply because in this particular course, we are focusing on gas phase reactions only. Okay, we are not considering liquid phase reactions. But we'll talk about each one of these and we'll talk about the chain reactions in the next class. For now, let's get started with the remaining parts. Now, when we talk about the direction of the reaction, we're simply saying that we're trying to understand whether a reaction is reversible or it only happens in a given direction. It only happens in the forward direction, for example, right? It turns out that a large number of elementary reactions can actually proceed in both directions, meaning they are reversible, okay? A very large number. Of course, the reaction rate for the reaction, both forward and backward, is going to be different, but it can take place, right? That's essentially what we are talking about here when we talk about elementary reactions. So when we talk about the reaction rates, of course, for backward and forward, as we said, they'll be different, but the key point is that they can still proceed. So if you're having a reaction like this, okay, reactants giving products, and both directions are possible, meaning that this here is a set of reactants, right? And it forms products, but the products then can also become the reactants and give this A1R1 plus A2R2 as a product. So it can proceed in both ways. So when you have a reaction which can proceed in both ways, when you're trying to write down the rate of change of any particular reactant, you have to take into account both the directions. Okay. So for the first direction, for KF, for the forward direction, R1 and R2 are the two reactants. Okay. And the rate of the reaction, the rate of the consumption, rate of change of this reactant R1 is going to be minus A1 uh, times Kf times R1 raised to A1, R2 raised to A2. Okay, simply indicating the dependence on the reactants for that particular for that particular reaction. But in the next reaction, which is the backward reaction, the reactants are P1 and P2. Okay, and the products are R1 and R2. So this particular reaction is actually leading to formation of the species R1. Okay, so therefore it's going to be plus A1 times Kb, the rate of the reaction, the backward reaction, times the reactant for Kb, which is P1 and P2, both of them raised to the stoichiometric coefficients. Now, obviously, this is something that we are writing based on the law of mass action, which applies to the elementary reactions. Okay, so this is essentially what we need to do, right? So if you're if it was happening in only one direction, if it was happening only in the forward direction, then I would not be writing the second part. I would just be writing the first term. But because it happens in both reactions, backward and forward, meaning the species R1 is consumed in one reaction and it's produced in the other, you need to write the entire. You need to write both of them here as shown. Okay, so this is what happens when a reaction is proceeding in both directions: consumption here and production here. Okay. Now, let's look at a practical example here for that particular case of reversible reaction. So if you have a S2 hydrogen molecule plus oxygen atom, it can lead to the formation of OH plus H. But OH plus H can also combine to give us H2 plus O, right? So you can write the forward and the backward reactions here. Okay, so this is the forward reaction, and the second one is the backward reaction. Okay, so when you're dealing with such reactions, and I'm trying to write down how the species H2, how the concentration for species H2 will change, well, it's simply equal to the rate coefficient for the forward reaction Kf times the reactants for that constant for that reaction, which are H2 and O, right? What is this part? And in this case, it's consumed, right? The H2 is getting consumed, so we have the negative sign here. Now, but on the other hand, when we look at this second reaction, H2 is actually on the product side, so it's being produced. So we write it as plus Kb, the rate of the reaction, the rate coefficient of the reaction, times the concentration of the reactants. The reactants are now OH and H, okay, and that's what we have here. Now, if we are having an equilibrium condition, then we know that for equilibrium, the concentration will not change, which means that the concentration of S2 with respect to time will be the change in S2 with respect to time will be zero, simply because S2 the concentration for that species is remaining constant. And if you set that to zero, what you get is the ratio of the reaction rate coefficients Kf by Kb is equal to OH times H by S divided by the concentration of S2 times O, which basically is equal to the equilibrium constant for that particular reaction, as we have seen earlier. Okay, so this is just a very simple example of a reversible elementary reactions. And as we said, a lot of elementary reactions are reversible. They can proceed in both directions. And as you can see from this reaction coordinate versus energy, they can proceed in the same direction. Does not mean they have same rates. They have to cross a different barrier, right? So if for a particular reaction in the forward direction, in this case, what we see here, the activation energy is small. In the reverse case, the activation energy is large. But still, at the right temperatures, at the right conditions, it can either direction can be more happening at a faster rate. Okay, so the key point is that it can happen both ways, which means that you have to take both options into account, the consumption as well as the formation for all species. Okay. So that's the first category, the first classification. Now, second classification is based on molecularity. Okay, so when we talk about molecularity, we are simply talking about the number of molecules that are taking part in the reaction, right? So if you have a general elementary reaction, A plus M times B giving the products, then the molecularity, right, is simply the total number of molecules that are participating in this reaction. Okay, or the total number of reactant molecules. So in this case, the molecularity is 1 for A and M for B. So the molecularity for the reaction is 1 plus M, as simple as that. M can be 0, M can be 1, M can be 2. Okay, so if you have a reaction like this, A plus B giving C plus D, I have the molecularity of this reaction will be 1 molecule of A, 1 molecule of B. So the molecularity will be 2. Okay. Same way, if I have A plus B plus C giving D plus F, the molecularity of the reactants, the molecularity of this reaction will simply be 3, because I have 1 molecule of A, 1 molecule of B, and 1 molecule of C. Total 3. That's all it is. Okay. It's as simple as that. Now we need to be careful that there is another term which tends to follow molecularity, and that's the order of a reaction. Now, order of a reaction is defined with respect to the reactant. Okay, it's not defined for a reaction. Molecularity is something that you can simply obtain directly by looking at the balanced chemical reaction. But when we talk about the order of a reaction, it is more of an empirical quantity, as it comes from rate law. Okay, it is simply the sum of the the coefficients that are shown up in the rate law. Okay, so it depends on which you may have a reactant whose concentrations are not changing much and is not contributing to the reaction, and it will uh, not contribute to the order of the reaction as well. Okay, so let's look at that a bit. So molecularity is very simple. You count the number of molecules and you have it. Okay, but the order, right? Order in this particular case, the order of the reactant is defined specifically. So order of reactant is 1 with respect to A, and it is M with respect to B. It can be 1, it can be 2, whatever, right? Now, when we as we discussed, the order of this reactant is not always or not necessarily related to its stoichiometric coefficient, right? Of the balanced chemical reaction that you may have. And a good example would be to say that when you have a bimolecular reaction, let's say C2H6 plus M, Okay, M can be any molecule, argon, helium, whatever. You have two molecules, right? This bimolecular reaction, it has two molecules, so it's surely bimolecular. It is right. It is surely bimolecular. But in terms of the order of the reaction, we cannot simply look at this and say, okay, let's say C2H6 plus M gives CH3 plus CH3 plus M. We cannot look at this and say it is second order. Okay. It is first order with respect to reactant C2H6, first order with respect to reactant M. But in terms of the order of the reaction depends on the rate law, right? And it's sort of formed empirically. You have to see what is the contribution of each of the reactant to the reaction rate. So, in essence, what we're trying to say is that a bimolecular reaction like we see here, it may be a second order or may not be a second order. Okay. Uh, when you just see two molecules, it does not mean that it is second order directly. But on the other hand, when we see a second order reaction, or when we know that the reaction is second order, it has to be a bimolecular reaction. Okay. So as just an example here, C2H6 plus M, it can behave like a first order reaction. You have two molecules, it is bimolecular, no doubt, but it's not second order. It can behave like a first order reaction. So in general, reactions behave like first order, and we'll see what it entails to say first order. Reactions behave like first order when one of the species is either so high that its concentration does not change, or it does not take part in the reaction, right? It's not its concentration does not affect the reaction much, essentially, reaction rate, sorry. So the only point I want you to know from here is that when we're looking at a given reaction, you can simply look at the balanced chemical reaction equation and look and see what the molecularity is, okay, without any confusion about that. Order of a reaction, it depends on the rate law, okay? Now, if you have a first order reaction will surely be a unimolecular reaction. Okay, so if you have a first order reaction, it can look something like this. A unimolecular reaction looks like something like this. You just have one reactant giving the rest of products. Okay, a second order reaction, which we said is always a bimolecular reaction. Okay, it's not the opposite. Bimolecular is not always second order, but second order is always bimolecular. A second order reaction should have two reactants, which are important, and its equation can look something like this. And same way, you can have trimolecular or third order reaction, and so on and so forth, like shown here. Now let's talk a little bit more about the first order or the unimolecular reaction. So let's say, okay, we have this reactant A, which is breaking down and forming two products. All right. And in terms of the order of the reactant, it's first order in terms of reactant A. Now, if I want to see the change of concentration of reactant A, or I can write the rate of change of reactant A as equal to the reaction rate omega. Okay, and this is equal to the reaction rate coefficient times the concentration of reactant A. All right. Now, in this particular case, the reaction rate coefficient or reaction rate constant has the units 1 per second. It depends, as we said, simply on the order of the reaction that we're dealing with. Now, I can simply write this as dA by A is equal to minus k dt. And when I integrate it, right, from a concentration A naught at time 0 to concentration AT at time t, I end up with an expression like this, which is log A at time t by A naught with this concentration of A at time 0 is equal to minus k times t. Okay, or I can write the concentration at any time t as equal to the initial concentration times exponential of minus kt, where k is the reaction rate coefficient or or rate constant, okay, which we get from Arrhenius equation. Now, when we are talking about any reaction, we are usually very interested in knowing the half order of the reaction. Okay, sorry, half life of the reaction. Sorry, and half life of the reaction is simply the time it takes for the reactant concentration to reduce to half of its initial value. So basically, we're talking about the concentration of reactant A being equal to half of the value at time 0, or A is or equal to A naught by 2, right? So when you use this particular formula, right? So we have log AT by A naught is equal to minus KT. I'm trying to find out what is the half-life, right? So uh, the time at which concentration AT is equal to A naught by 2. I can simply write it as T half is equal to ln A naught, what is this part, minus ln A naught by 2, which is the value of AT at that particular time divided by K, or which comes down to 0.693 by K. So half-life for a first order reaction can be directly written as 0.693 by K, right? And there are many reactions which fall into this category of unimolecular reaction or uh, first order reaction. You could think of decomposition or dissociation or isomerization. I've given an example of isomerization, which is simply rearrangement of molecules, and you start with one molecule and you end up with one molecule, right? So this is a good example of a unimolecular reaction or a first order reaction. But in reality, unimolecular reactions are kind of it's an idealization because you need sort of two molecules to collide and form products usually, right? And so molecules do not disintegrate spontaneously by themselves. So in a lot of cases, we need a third body, okay? And especially when we're talking about decomposition, for example. So we need a third body simply to take part in the reaction, but this third body, uh, in the sense when I say take part in the reaction, it's just contributing to the collisions part, right? It is not really reacting, okay? The concentration of third body remains same, both on the reactant and the product side. So like the example we saw, okay, C2H6 plus M gives CH3 plus CH3 plus M. So we have M on the reactant side, we have M on the product side. This reaction will not proceed without having M on both sides. Of course, you need M for the third body for the reaction to proceed, but the third body does not participate in the reaction. All right. So this, although it's a bimolecular reaction, it can very well behave like a first order reaction, simply because the concentration may depend only on the concentration of C2H6 and not on the concentration of M. Okay, so this is an example of a first order reaction, which is bimolecular, but you can also have first order reactions which are unimolecular, but unimolecular first order reactions are rather small, or essentially unimolecular reactions are rather small, okay, because you're just talking about one molecule rearranging itself, which doesn't happen very often. All right, so now let's talk about second order reaction. And second order reaction have to be bimolecular at a minimum, right? So if we have, let's say 2A giving rise to two products, or 2A is essentially A plus A giving products B1P1 plus B2P2. Then with respect to A itself, it's second order. And of course, when you write it in differential form, the rate of change of concentration of A with respect to time dA by dt is going to be equal to the reaction rate again. But this now is equal to the rate constant times the concentration of the reactants raised to its stoichiometric coefficient, which is A squared, right? And again, when you integrate it, you get the 1 minus A naught minus 1 by T is equal to minus KT, where AT is simply the concentration at any time T, uh, and A naught is concentration at time 0. Okay. Now, just like we did in the first case, we are interested in finding its half-life. We want to find out after how much time, after how many seconds, the concentration reduces to half of its initial value. When we do the same, when we follow the same method, that is, we set A as equal to A naught by 2 at T is equal to T half, then you get T half as 1 by K times A naught, right? So it depends on the rate constant, of course, but it also depends on the initial concentration. Okay, so if we sort of compare this with the first order reaction, in the first order reaction, it did not depend, the half-life did not depend on initial concentration, right? It just depended on K. Okay, so you can see that this half-life only depended on K for first order reaction. Okay, but when you're dealing with a second order reaction, well, it depends on the initial concentration as well in this particular case. And thinking about it, bimolecular reactions are actually the most common kind of reactions because you're having two molecules, and so the collision probability is, of course, very high. Okay, Now, you can also have a third order reaction or a trimolecular reaction where you have three molecules combining together to form some products. And For the third order rate law, you can simply follow the same method and write it as minus K times R1, R2, R3. This is the unit for K. As I said, it depends on the order of the reaction. Now, when we talk about third order reaction or a trimolecular reaction, the trimolecular reactions are rather rare, right? You it's very common for two molecules to collide, but it's not so common for three molecules to come together, right? That's sort of a relatively rare event, and it usually requires high pressure, or it requires yeah. I mean, you can see that possibly in the reaction of um, some ions or atoms with some molecules, right? It's kind of a rare event. It's not so common. The most common is, of course, the bimolecular reaction. Okay. Now, cases where we have a trimolecular reaction usually involve a radical or an atom, uh, which basically means very reactive species. So an example could be the combination of OH and H along with maybe a third body to produce H2O. We can have OH plus H plus M, giving H2O plus M. Now, as we said before, in a lot of reactions, we need third body simply to take care of the collision and to absorb some of the energy, right? In this particular case, these reactions are exothermic. The recombination of OH and H are exothermic. And so we need the third body to take care, to participate in this reaction and take care of some of the excess energy that's produced.